do you have access to my
yes,
to my screen?
Yes, you can start.
Okay. Oops. Oh, sorry. So the topic of my presentation is the effect of aging on the corrosion-induced degrees of plane stress fracture toughness of aluminum copper lithium 2198 alloy. Aeronautical aluminum alloys are widely used in aircraft structures due to their lightweight, their high corrosion resistance, increased damage tolerance, the low cost, and in general, the major manufacturing processes. Third generation aluminum copper lithium alloys, such as 2198, were developed to overcome some disadvantages of the conventional aluminum copper alloys, such as 2024. And these aluminum copper lithium alloys are preferable due to their low density, their high last modulus, high specific strength, and the good corrosion resistance. Aluminum copper lithium alloys are heat treatable and their mechanical properties can be significantly improved by heat treatment processes. Their major, their major strengthening phase is the T1 with, I don't know why the slides are going to the next. Excuse me. Is it possible to see to present like this? Can you see?
Yes, I can zoom your screen, no problem.
I don't know. There is a problem with the.
Okay, you can in this manner, no problem.
Okay, and as I was saying, their major strengthening phase is the T1 phase with a composition of aluminum to copper lithium and the hexagonal crystal structure. And as was revealed by previous studies for other aluminum copper lithium alloys such as 2050, these strengthening phases tend to increase both in density and size with increasing artificial aging time. One of the most common and dangerous damage problems on aircrafts is the corrosion, as was also revealed by a research conducted on a Boeing 747. 2000 series aluminum copper alloys are highly susceptible to localized corrosion, which is usually caused by several damages and flaws on the protective surface layers or surface heterogeneity, and due to microstructural transformations coming from aging and machining processes. The target of the present research is, as I already mentioned, that the several microstructural transformations which take place, for example, usually during aging of these alloys, the alloys that are aged were found to be highly susceptible to corrosion, and usually intergranular fracture mechanisms are observed in this kind of alloys, in the aged alloys. So it is of crucial interest for the aircraft maintenance protocols to estimate the corrosion behavior and the corrosion mechanism in old aircrafts. The experimental procedure of the present work included artificial aging, isothermal artificial aging at 107 degrees Celsius, and corrosion exposure to EXCO solution, then fracture toughness testing and microscopic analysis of the specimens. In this slide, Also, the configuration of the specimens is presented, and and how the surfaces were covered in order to be exposed to the corrosive solution. The corrosive solution that was selected was the exfoliation corrosion because it is a very aggressive solution that better stimulates a pit and corrosion mechanism. And since regarding a previous work of our team, it was found that only 24 hours exposure to corrosion, to exfoliation corrosion solution were needed in order to have the same degrees of elongation of fracture that is shown in this figure, with approximately 6 months of the same exposure at sodium chloride solution. And regarding the specimens that were artificially aged, the time of exposure to the exco solution that was selected were the 2 hours, because in a previous work of our research team, it was found that, for example, for 2024 aluminum alloy, a significant strain decrease was noticed after only 2 hours exposure to this solution, shown with the blue curve, while not so significant stress drop, where the stress drop was found to be a combination of hydrogen embrittlement and degrees of the cross section of the specimens. And for the calculation of the critical stress intensity factor, firstly, the raw data of load versus crack mouth opening displacement of the specimens were used, from which the R curves were extracted through a compliance method, as it is shown according to the ASTM standard. Then the value of the crack growth resistance at the instability condition determined from the tendency of the R curve with the several applied K curves of the specimen. Summarizing with the experimental procedure, in total 3 cases were investigated and are presented in this presentation. The first case includes the effect of corrosion on 2198 in the T3 condition, where several different corrosion exposure times were used. The second case includes the effect of artificial aging on 2198 received in T3 temper, where the specimens were exposed to different artificial aging times, exposed to 170 degrees Celsius for different aging times. And the third case, the case 3, is a combination of the previous cases, includes the effect of artificial aging on corrosion and the already artificially aged specimens at several hours, representing the several stages of aging, were exposed to, as I also referred to, 2 hours to expo solution. Moving to the experimental results of case 1 regarding the effect of corrosion on fracture toughness, by representing the raw data of load versus the CMOD, it was noticed that the maximum load decreases with increasing exposure time to exco solution. A significant decrease of load was noticed after only 2 hours, represented by the red curve, while for higher exposure times up to 12 hours, this decrease was not essential. A sudden drop is again visible after 24 hours. Additionally, no significant reduction of the crack mouth opening displacement at the maximum load was noticed up till 24 hours. Regarding the surface deterioration and the morphology of the corroded specimens in T3 condition, it is obvious from the pictures that for 2 hours exco exposure, the surface deterioration remains limited. The pre-cracking was not drawn as a straight line to the loading axis, and its morphology was not completely the same on both sides of the specimens. Additionally, in some cases, the formation of double crack was noticed. Regarding the specimens exposed to 24 hours exco, several pits in higher density and size were noticed in the surface just in front of the crack line, and it seems that the crack follows the path of these corrosion pits. Regarding the effect of corrosion on the K-critical stress density factor, the K-critical was found to decrease with increasing exco time, where an essential decrease was noticed up till 6 hours. While for higher exposure times, the K-critical was almost stabilized, and then a sudden drop was also noticed after the maximum exposure time to exco solution, the 48 hours. The trend of the reduction of K-critical with increasing exposure time seems to be almost similar to the trend of elongation of fracture decrease. Nevertheless, the elongation of fracture was found to be continuously decreasing with increasing exco time, and it reached almost 50% degradation after only 12 hours of exposure. So moving to the other two cases, firstly to the case of the effect of artificial aging on fracture toughness, it was noticed that with increasing aging time, a gradual decrease of maximum load and crack mouth opening displacement was noticed. However, a short increase in maximum load was evident after 98 hours, represented with the magenta color in this figure, and also a small recovery of the crack mouth opening displacement was noticed after 400 hours aging time. Regarding the effect of aging on corrosion, the aged specimens were then exposed to exco solution for 2 hours and are shown in the right figure, where it can be noticed that a higher degrees of both the maximum load and the crack mouth opening displacement at maximum load is evident for the T3 and the first hours of aging time, for instance, 3 hours, while not significant differences due to corrosion exposure were noticed for the higher aging times. And regarding the evaluation of the critical stress density factor of the aged specimens that were further exposed to exco solution for 2 hours, it was noticed that the critical stress density factor was significantly affected by artificial aging, represented by the black curve, where approximately a 50% decrease was noticed at the peak aging regime. And then the K-critical was slightly recovered. Nevertheless, significant degradation due to 2 hours exo-exposure was noticed, represented by the red curve. And this degradation was higher for the underaging regime, and for example, up to 8 hours, while for the peak-aged and overaged times, this corrosion-induced degradation was found to be minimum. So reaching to the conclusions of this presentation, the critical stress test factor of aluminum alloy 2198 in T3 condition is essentially reduced due to corrosion exposure. And the critical stress test factor was also found to be essentially affected by artificial aging, where a degradation of up to 50% was noticed for the peak-aged specimens. However, the effect of corrosion on the K critical was found to be different for the different artificial aging times and tempers, and more significant for the underaged specimens. This work was funded in the framework of a national research project, corrosion susceptibility, degradation, and protection of advanced aluminum lithium alloys by the Hellenic Foundation of Research and Innovation. Thank you for your attention.